Hello friends, welcome to part 2 of mechanics question paper solve 2019 of Dibrugarh University, set by Dibrugarh University for BSc first sem physics honors. So this is paper C2. So now in this video we are going to solve from question number 3b, because in the first part we have solved from question number 1 to 3a. Now we're going to start from 3b. So before we start, please subscribe the channel if you are new to my channel, and share the videos with your friends, and also like the video. That means hit the thumbs up button and also hit the bell icon so that you get notified when new video will be uploaded. So now let's start. So this is question number 3b. So state work energy theorem. Also draw energy diagram for potential energy and kinetic energy and total energy for the case of spring. So now what will be the answer here? So work energy theorem. So let me write the first work energy theorem. Let me write this one. So this theorem states that the total work done by the sum of all forces acting on a particle is equal to the change in kinetic energy. So this is the work energy theorem, right? So now let's go to the diagram of energy diagram for the potential and kinetic energy and total energy for the case of spring. So let's move on to next slide. Okay, so energy diagram for potential, kinetic and total energy case of spring. So this should be, the diagram should be like this, right? So this red one represents this red one represents potential energy and the green one represents kinetic energy, and total energy is the nothing but sum of this to potential and kinetic energy. So here this is x, and E represents total energy. So this is energy axis, right? So here you see total energy is given by kinetic energy, sum of kinetic energy and potential energy. So T represents kinetic energy, T represents kinetic energy, right? And potential energy is represented by V, right? And this axis represents displacement, and here this is energy. This vertical axis represents energy, and total energy is nothing but sum of for kinetic and potential energy. So hope you have understood this. Now let's move on to next question. So here you see this question is also 3b, question number 3b. So either you can solve the first one or this one. Okay, two questions were given, you have to solve any one of these two. So here, prove the principle of conservation of energy for the freely falling body under action of gravity. So we have to show that energy is conserved. Okay, so we have to take an example of a freely falling body. So principle of conservation of energy. Okay, we have to prove that one. Kinetic energy plus potential energy, that is constant. That's what we're going to prove, right? So this is a particle, or you can consider an object, freely falling object from a height h, and its mass is suppose m. So this is the ground, right? That is falling. Suppose an object of mass m be falling, be at a height h from the ground at position A. We have considered this position as A before it was allowed to fall, right? So potential energy at this potential energy before it is allowed to fall, it must be mgh, right? And before it was fall, there was no velocity, that's why kinetic energy must be equal to 0, right? So total energy, kinetic energy plus potential energy gives mgh plus 0, that's going to be mgh, right? So total energy is mgh at this position A, right? So now you see, now it is suppose allowed to fall and reach the position B. Okay, so it reached the position suppose B, this position is B. So at this position, to reach this position, the object covers a distance of x, suppose, right? Then if it covered a distance of x, then height from the ground is now h minus x, right? So it is allowed to fall, and at b, so v naught, initial velocity before it was allowed to fall, v naught is equal to 0, and now vb, at position vb, the velocity is suppose v we have taken, and distance or displacement you can say here x, right? So we know this formula, 2gx v square minus v naught square. If you apply that from here, g is the acceleration due to gravity, you know that, right? So from here we can calculate, if you put the value of v naught, initial velocity, which is 0, then you will get 2gx v square, right? This is equation number 1, suppose. Now you see, if you calculate the kinetic energy, that's half mv square. If you put the value of v square here, then what you are gonna have, so here 2 to cancel, right? So mgx, kinetic energy is mgx. Now let's calculate potential energy. So now it is at a height h minus x, so potential energy is mg h minus x, right? Now if you find the total, let's find the total energy adding the kinetic and potential energy, then what you will get, so here mgx minus mgx will be cancelled, so only mgh left, right? So total energy will be mgh. So here I have used equation number 1. So in this equation, this one used from equation number 1, so mention it. Okay, I forgot to mention that. So now you see, this equation number 1 is used here, v square, right? Value of v square we have got from equation number 1, right? So now let's move on to next slide. So here at the position we have got the total energy E, mgh. At position B also we have got mgh. Now let us consider, this is, let me draw the diagram again. So it is falling down, right, B, and this position is suppose C, just before touch the ground. This is C, suppose this is a position just before touch the ground. So velocity, before velocity becomes 0 after touching the ground, so it is such a position where velocity is maximum, right? Just before touch the ground. So then what will happen? Now let us consider here, at this here height is 0, so potential energy will be 0, right? So now 2gh v square minus v naught square, so v naught will be 0 because before it was allowed to fall v naught, that means initial velocity was 0. So from here what we will get, v square is equal to 2gh. This is suppose equation number 2. Now kinetic energy half mv square. Now put the value of mv square, v square, from this equation number 2. So then what you will get, kinetic energy half mv square, instead of v square we're going to put gh, 2gh, 2 to cancel here, so we got mgh, that is the kinetic energy. And potential energy, as the height is 0, potential energy will be 0. So total energy, adding the potential energy and kinetic energy. So here you see, adding these two energy, potential energy and kinetic energy, this is the kinetic energy, we have got total energy is E is equal to mgh. Now you see, let me say the energy at the position, total energy at position A, so let it be suppose E1, and at B it is suppose E2, and at C, at this point C, so this is suppose E3. This is the total energy at C, E3. So if you see all the three energies at all the three positions, total energy is equal, E1, E2, E3, these are equal, all are equal to mgh. Total energy is same. So we can say potential energy plus kinetic energy, that is total energy, is equal to constant. So that is what we need to prove, right? Now this is question number 4. Here you see, so that the rate of change of angular momentum vector of a particle is equal to the torque acting on it. So we need to show that the rate of change of angular momentum dl by dt is equal to the torque acting on it, right? Need to say, so the torque acting on it. And we also it is also asked that for what kind of motion that angular momentum will be 0. So that is asked here. So suppose here you see we have a particle moving. This is a particle. It's a, suppose position vector is suppose r, so x, y, and z. So moving in a suppose circular path or rotating about an axis. So it must have an angular, momentum, and it's a linear momentum at this point. Suppose this is p, vector p represented by vector p, then the angular momentum of the particle. So we know that answer angular momentum of a particle is vector L is equal to cross product of its position vector and linear momentum, right? So here P represents the linear momentum. P is the linear momentum. Now if you differentiate this equation, let me differentiate this equation number 1. Differentiating equation number 1 with respect to t, time t, and what we get, if you differentiate this equation, you will get dl by dt, that's going to be equal to dt of r cross vector p, right? So then that's going to be equal to, if you use the product rule, r cross dp by dt plus then dr by dt cross p, right? That's what you're gonna have. So this is suppose equation number 2. This is suppose equation number 2. So now what we are going to do now, here you see dr by dt is the velocity and dp by dt is the rate of change of linear momentum of a particle at any instant. So here dr by dt is nothing but is the velocity and dp by dt is rate of change of linear momentum at any instant. Okay, at any instant. Right. Now this equation number 2 can be written as now you see here you have got that as here you have got this dr by dt is nothing but velocity, so you can replace dr by dt by velocity v, and we know the linear momentum is nothing but mass into velocity, so you can replace this by m into v, and rate of change of linear momentum gives the force acting on the object, right, F. So that's why this equation number 2 becomes let me go to the next slide. So equation number 2, therefore the equation number 2 can be written as, so the dl by dt is equal to that r vector cross dp by dt plus v, that is velocity, cross m into v, right? So what does v represents here? dr by dt, and m into v is the rate of this is the linear momentum, right? This is the linear momentum p. So rate of change of linear momentum dp by dt is equal to the force F, that is the force acting on the particle, right? On the particle, right? So that is why what we can do, we can replace this one by F, right? So this equation number 2 can be written as del L by del T is equal to R vector R cross F, right? So it's a vector quantity plus V cross M into V, right? You can write that way. So position vector, this R cross F gives the torque acting on the particle, okay? This cross product gives the torque acting on the particle, or you can say moment of force. So this is nothing but torque or moment of force. So where tau, this is equal to R cross F, right? This is called moment of, this is torque, this is called torque or moment of force, right? So we have got this. Now you see these two, velocity and the momentum, these are parallel, okay? They are directed in the same direction. So this is linear momentum and linear velocity and linear momentum, so they are parallel. That's why cross product of these two will be 0. Cross product of these two will be 0, since the cross product of two parallel vectors is 0. Therefore V cross M into V will be equal to 0. Therefore what we have got, rate of change of angular momentum del L by dt is equal to torque. So that is what we needed to prove, right? So the next part of this equation is given that if you see the next part here, you see, so what kind of motion you expected from L is equal to 0. So what kind of motion we expect from this? Now you see this vector L, that is angular momentum, is equal to 0 means, now you see angular momentum L is equal to R cross P, that gives the angular momentum of a particle which is moving with suppose linear velocity v of mass m. This angular momentum, that R cross P, gives the angular momentum about a point with respect to which point the position of this particle is R, right? So now you see this L cross R will be R cross P will be 0 when this R vector and V vector are parallel, and that will be possible. That means the point about which we are calculating the angular momentum, if that point lies on this line in which it is moving, right? So that means it is possible if the particle is moving along the line which, so, or you can write along the line passing through the point about which the angular momentum is calculated. And in this case, this position vector of the point about which we have calculated the angular momentum must be parallel to this its linear velocity v, or parallel, right? So now let's here you see, let me write this also. So r is equal to r cross linear momentum p, so which can be written as r cross m into v. So m can be written outside, so you can write r cross v, right? So if these two are parallel, then only it can be 0 if r parallel to vector v. So hope you have understood this. Now let's move on to next question. So our next question is question number 4b. So for a rotational motion of a rigid body, derive an expression for kinetic energy in terms of moment of inertia. So let me give you the answer of this part first, okay, and also angular velocity in terms of moment of inertia and angular velocity. So let me write the answer of this part first, then I'm going to give you the answer of the next part, that is also obtain an expression for the moment of inertia of a circular ring about an axis passing through the center and perpendicular to the plane of ring. So first let us do the first part. Now let us answer this question number 4b, right? So here you see, suppose we have a body of mass m, capital M. So this is the body of mass capital M, and it is rotating with angular velocity. Omega about this axis of rotation. This is the axis of rotation, you can see here. This is the axis of rotation through O, right? So now you see, we have considered that this body consists of very small tiny particles. So suppose this is one particle of mass m1, right? So it is m1, and this is another particle, suppose m2, okay. So they are respectively at a distance of r1 and r2 and so on. So there are large number of particles m1, m2, m3 such that, and at a distance r1, r2, r3 from the axis of rotation. We have considered that way, right? So now as the body rotates, all the particles of the body have the same angular velocity, because these small particles composed by this object will be rotating with the same angular velocity omega with which this rigid body is being rotated about the axis, right? So now let us consider that v1, v2 v3 etc. be the linear speeds respectively of mass m1, m2, m3 and so on, etc. So then the kinetic energies of the particles of having mass m1. So we know that kinetic energy of a particle is given by half mv square, where m is the mass of the particle, v is the velocity, right? Or you can say linear velocity. So now that kinetic energy of the particle mass m1, then the kinetic energy of the particle having mass m1 will be given by half m1 v1 square, right? And v is equal to r omega, right? V is equal to r omega, so v1 will be equal to r1 omega, right? So similarly, kinetic energy of the particle mass m2 will be half m2 r2 square by omega square into omega square and so on, right? So if you find the total energies, then you have to sum up the energies of m1, m2, m3 particles of mass m1, m2, m3 and so on. So adding all those, here we have got half m1 v1 square, half m2 v square, half m2 m3 v3 square and so on. Now you see, again if you replace v1, v2, v3 by r1 square omega square, r2 square omega 2 square, omega square, r3 square omega square, and we have got those, and then omega square and half is taken common, then within bracket we have got m1 r1 square, m2 r2 square, m3 r3 square and plus so on. And here this sum of this m1 r1 square plus m2 r2 square, m3 r3 square can be written this way, summation m r square, right? Summation m r square, m r square, right? So, and this is nothing but moment of inertia I, right? So we can replace this term summation m r square by capital I, which represents moment of inertia. So thus the total kinetic energy of the body is half I into omega square, where I is the moment of inertia of the body about the axis of rotation, and the translatory kinetic energy of the body of mass capital M is half mv square. And a comparison of two expressions shows that in rotatory motion the mass capital M is replaced by the moment of inertia I. So in translatory motion, here you see the kinetic energy is given by capital half mv square, right? Here m is the mass of the rigid body. So if you compare these two expressions, right, here I is m is being replaced by I, that's half I omega square. Finally we have got this expression, right? And this v square is replaced by the angular velocity omega, right? This v is replaced by angular velocity omega, right? And here you see, so finally we have got, let me clean this. So finally we have got the total energy as total kinetic energy E is equal to half I omega square, right? So let me write this one properly. So we have got E is equal to, that is total kinetic energy I omega square. So what was the question? Here you can see the expression, derive an expression for kinetic energy in terms of moment of inertia and the angular velocity. So we have got this expression of kinetic energy of that body in terms of moment of inertia I and angular velocity. So hope you have understood this. Now let's move on to next part of this question. Here you see, also obtain an expression for the moment of inertia of a circular ring about an axis passing through the center and perpendicular to the plane of the ring. So now let me give you that answer. Now moment of inertia of thin circular ring about an axis passing through the center O, of this circular ring perpendicular to the plane, right? So about an axis, it is passing through the center O, which is perpendicular to this plane, right? This is perpendicular to this plane. That means, so this is the plane where the circle is lying, and this line which is passing through the origin, that this line which is passing through the origin is perpendicular to this plane, right? So hope you can imagine that. Now you see, let r be the radius of the circular ring and m be its mass. If we consider particle of mass m, so we have considered a particle of mass m, which is at a distance of capital R, which is equal to the radius of the ring from the center O, right? And it is considered on the ring, okay? And the moment of inertia of the particle about an axis passing through O. So the moment of inertia of this particle m, which is passing through about the axis passing through this origin O, is given by m into r square, right? That's given by m into r square. Now if you consider that this ring consists of large number of such particles, very large number of such particles of mass m, then the moment of inertia of entire circular ring will be given by the sum of moment of inertias of all these particles, right? So that's why, since the ring is made up of large number of such particles, the moment of inertia of the entire ring will be the summation of the moments of inertia of all such particles. Hence the moment of inertia of the whole ring is given by I is equal to summation m r square, right? So moment of inertia of one particle is mr square, then the next one is also mr square, and if you add so on, then you will get summation m r square, and summation m is the mass of the whole ring, that is capital M. So that's the expression for the moment of inertia of a circular ring about an axis through the center, and about an axis through the center which is perpendicular to the plane of the ring. So that's how we can solve. So hope you have understood this. So our next question, so that for a satellite moving in a circular orbit, the square of the period of revolution, that means you can say time period, is proportional to the cube of the distance from the center of the earth. So here let me tell you something. Suppose we have considered so let us consider a satellite in a circular orbit, concentric and coplanar with the equator of the earth revolving. Satellite is kept in a circular orbit by the force of attraction between the satellite and the earth, which provides the necessary centripetal force. So that means, so now you see, suppose we have a circular orbit. Suppose, let me draw a circular orbit around the earth. This is the circular orbit, right? So here, this is the earth, this is the position of the earth of mass me, and the satellite, this is of mass small ms. So it is revolving around this earth, which is at a distance of r from the earth. And now you see, the force which keeps this satellite moving around the sun is the gravitational force between these two, right? Gravitational force between the earth and this satellite, right? So which is given by F is equal to capital G capital M E small m s by r square r cap. So r cap is the unit vector along the radius r, right? We have considered it way, and here capital Z is the universal gravitational constant. Universal. So let me write properly. Universal gravitational constant, right? So now you see, this is the unit vector of the so let me so r cap is the unit vector of the position vector of the satellite relative to the earth, right? So now you see, unit vector of a vector, suppose unit vector r cap of a vector r is given by vector r divided by its magnitude r, right? So if you use this relation here, then what you will get, this result will be f z. Here you see, so here I forgot to put a minus here. This minus sign indicates nothing but this is the gravitational force between these two is attractive, right? That's what it represents. Okay, so now let me write here in vector form. Here you can write minus z capital M E. So Me represents mass of the earth, ms by r cube, r cap. That is what we have got. This is suppose equation number 1. Let me write this one on the next slide also. So here is the equation number 1, right? This is equation number 1 we have taken again. Now if v and omega respectively are the linear and angular velocity, so v is the linear velocity and omega is the angular velocity, then you say v is equal to r omega. That is the relation between angular velocity and linear velocity. Now the centrifugal force is given by F is equal to minus mv square by r. Now if you use this relation here, then you will get minus m omega square r square by r, and by r. If you cancel this r square by r, then you will get minus m omega square r. So if you, as we have considered mass of the satellite is ms, so here we're gonna write ms. So this is what we have got. Now this is our equation number 2. So here you can see this is the equation number 2 we have got, right? So now you see, let me clean this part. Now from equation number 1 and 2, from these two equations, equation number 1 and equation number 2, right? So from 1 and 2, what we get? So you can write this right hand side of this equation equal to right hand side of this this equation. So minus, you can write minus ms omega square r is equal to minus capital Z capital M small a ms by r cube. R vector is there, right? You can write it. So that's what you can write. So here is also you have r vector. So if you write in the if you write the centripetal force in vector form, there should be r vector, right? So here you can see that what we can write, that so you can see clearly what are the terms can be cancelled out each other. So ms gone, r gone. So we have got here minus also gone. So omega square is equal to capital Z capital M E by r cube. That's what we have got. So this is the equation number 3. This is the equation number 3 we have got. Now you see, if you consider that v naught as orbital velocity, okay, orbital velocity, then omega will be given by v naught by r, right? So if you use that in equation number 3, then you will get this relation v naught square by r square, g capital M E by r cube, right? So if you cancel r square r cube, then there will be r only. So after using this relation, we have got this now. So here you can see we have got this relation v naught square by r square is equal to capital G M E by r cube. You can see here. So now you see, let's cancel here. So here you will get r only. So v naught will be equal to root over capital G capital M E by r. That's the equation number 4. So this is the orbital velocity denoted by v naught, right? So now angular velocity omega is also given by, if you express this one in terms of time period, it's given by 2 pi by capital T. Capital T is the time period, right? Or period of revolution, you can say, of the satellite. So that is capital T. Then omega is equal to 2 pi by T. So here you see, if you use this expression in equation number 3 again, what we're going to use, omega is equal to 2 pi by T. If you use here, you're going to get this relation. And from this relation, what you will get? You will get T square is equal to this. So this is what we have got. T square is equal to 4 pi square by capital G M E into r cube. That's what we have got. This is the equation number 6, right? So this is the equation number 6. And from here you can see that this part of this equation, this part 4 pi capital G M E, here 4 pi square by capital G M E, this is constant. This part is constant, right? This part is constant because mass of the earth is fixed, and G is the universal, capital G is the universal gravitational constant, and pi is also a constant, 4 is also a constant. So that's why from this relation you can clearly write that T square is directly proportional to r cube. T square is directly proportional to r cube. That is why that is what we needed to show. The square of the period of revolution of a satellite moving in a circular orbit around the sun, sorry, not sun, earth, is proportional to the cube of its distance from the center of the earth. That is what we needed to prove. So hope you have understood these things. So now we have another part in this question. So next part of the question, here you see, what is geosynchronous orbit or geostationary orbit? So let me define this. So a geosynchronous orbit is a prograde low inclination orbit about the earth having the time period 23 hours 56 minutes 4 seconds. So this is the definition of geosynchronous orbit. So hope you have understood what I have explained in this video. So if you have understood, please share with your friends and hit the thumbs up button. And if you are new to my channel, please subscribe the channel. So in this video we have solved up to question number 4C. This question is 4C. Let me tell you this one. This question is 4C. There is another part, or instead of this question you are given another question that will be discussed in the next video. Okay, so stay connected. See you in the next video. Thank you for watching.